Welcome to the first meeting of Chem 100. Looks like we got a couple people here. I'm Patrick Lloyd. I'm going to be the instructor for this course. And I'm going to just talk a little bit about myself for a moment, and then I'll open up the floor to any questions you have. And then I want to cover a little bit of material from chapter 1 of our course today. So I'm the instructor for Chem 100. I also teach Chem 1100. So there's a good chance that you're taking this course because you need to take Chem 1100 and maybe even Chem 1200. This course is really intended as an intro to chemistry so that when you get into Chem 11, you don't get so overwhelmed with all of the material that gets kind of thrown at you. So what we're going to focus on is a little bit of chemistry and a little bit of problem solving, learning how to do problem solving. I suspect most people that are taking this course want to work either in engineering or in the medical field. And in the medical field, a lot of the courses you take in biology are really focused around taking in a lot of information and then explaining what you understand. Here it's going to be a lot of problem solving, at least in Chem 1100 it will be. So we'll get a little intro into problem solving in this course. Okay. I'm gonna have a weekly meeting on Mondays. I will apologize for the late notice on this, but actually I didn't find out I was teaching the course until Friday. But each Monday I will record the meeting. So if you can't make it, you can watch the recording on YouTube. But if you can make it, it's a great opportunity to ask questions directly to me. And then I always prioritize questions about the material over introducing new material. So if you have questions, I'll prioritize that. Okay. So the syllabus is on Blackboard in course documents, so make sure you review that. I did post a link to a video for the syllabus going over it. There were a few little typos in the syllabus in the video, which you may have noticed, but I cleaned all of those up and then reposted the syllabus into Blackboard. So it should be pretty accurate right now. Okay. Most of the work that you'll do, almost all of the work you'll do is submitted using that Alex software. So I put a couple of links on how to register, how to get started on it. This is the system that we use not only for the homework, but also for the exams, for the 3 exams that you'll take. So you really want to dedicate your time to Alex. Okay. Any questions so far? Okay. So what I'll do then is I'm going to go ahead and get started. Because so much of the work that you do in this course is on Alex, and it's undoubtedly a new system to you, I want to give you some experience in kind of seeing what the problems are like in Alex. So what I'll do today is I'm going to start on the first. So we got start coming in. I'm going to start by looking at chapter 1. Okay. Which is Chemistry, the Central Science. We got a few new people coming in here, so before I actually start on chapter 1, I want to take a moment just to welcome everybody. So we got a few more people that just came in. Welcome here. And just a reminder that the link, the number 761-534-4943, and the password meet, that'll be the same for the whole semester. So if you ever want to get in touch with me on Zoom, that's the way to do it. Okay. So for those of you who just joined, we just talked a little bit about about what the course is and the importance of signing up and registering and starting on this Alex software, okay, because the whole grade essentially is going to be based on the work that you do on Alex. And so you want to get working on that as soon as you can. Any questions starting off? Something. Okay. All right. So let me go ahead then, and I'm going to go ahead and start with chapter 1. Chapter 1 is just an introduction to this course into chemistry, but it does go into a few different topics. So let me minimize the screen so I can see if anybody is coming in. Okay. There we go. Now I can sort of see everything. Okay, so we're going to start with chemistry, which is the central science. This is on Alex, and I'm going to start by looking at a couple of the problems that involve understanding the idea of physical properties. Okay, so I'm going to start by talking about how we have what are called states of matter. Okay, and most people are probably pretty aware of that we have what are called solids. And solids, I'm going to draw a little diagram here to kind of represent a picture of a solid. So these could be atoms, or they could be molecules. And in a solid, typically the way we represent this is that the atoms or the molecules are very closely spaced with one another. So they're right on top of each other, touching each other essentially. Okay. So we would call this a highly ordered material. Okay.
Got it? Homework, week homework will be due by Friday.
Okay. And then we have what are called liquids. And liquids are also pretty tightly held by each other. They're pretty close to each other. The atoms are pretty close to each other, but they're more randomly distributed typically. So there's less order, they're more random. But we also know one thing about liquids that's different from solids, and that is that they're capable of moving with respect to each other. So one atom can move and at one point be near these other atoms here, but later on it might be near these other atoms over here. So there's a type of motion that is possible with them. Okay, let me come back here. I'm just going to check something. Okay. Okay. And then we have what are called gases. And gases are widely spaced. They're very far. The atoms are really far away from each other. Okay, so you see the big distances there between them. Okay. Let's see. Joining. Okay, got one more joining. Okay, so large spaces between the atoms or between the molecules. Okay, and one of the things that we can do is we can do what are called phase changes. Okay, now a phase change is where one a matter in one state can be converted into a different state. Okay, so for example, we might have something that's in the form of a solid, and we could convert it into a liquid. Okay, this process is called vaporization. I'm sorry, not vaporization, melting. Okay, so when a solid is converted into a liquid, that's called melting. And the way that we do that is by adding heat. At least that's one way to do it. So imagine that you have a container. Well, let's use something that we're all familiar with, ice cubes. Okay. And what we're going to do is we're going to take a little flame, like from a match. Okay. And we're going to produce heat. All right, we're going to transfer heat into the ice cubes. Well, as that heat is transferred in the ice cubes, the atoms in the solid will move faster and faster and faster until finally they will start separating and moving around each other. And so they'll undergo a process where they turn into a liquid. So now you have liquid water. So heat is the way that we do that. And that's called a phase change. So the phase change of going from a solid to a liquid is called melting. There are other phase changes. So I'm going to list a few of them for you. So solid to liquid. That's called melting. A liquid being converted into a gas, this is called vaporization. We vaporize a liquid into a gas. This requires heat, just like melting does. Okay. Both of those require heat. We can also go from the solid directly into the gas. Okay, that's also a possibility. And this is called sublimation. And sublimation also requires heat. So there are three different what we call phase changes. A phase is a type of matter. So a solid is a phase or a state. Sometimes we call it a state. Liquid is a different phase. Gas is a different phase. They can exist with each other. So for example, if you have ice cubes in liquid water, you have two phases right there. In fact, there's actually all three are there, because in an ice cube with water, there is a little bit of vapor of water. So all three phases actually coexist. We can also do the opposite. We can go from a gas all the way down to a solid. And this is called deposition. You're depositing a solid from the gas. This actually releases heat. Heat is actually released when this process happens. So imagine water vapor and then you have a cold surface, like you have a freezing surface. The water vapor, when the molecules of water collide with the surface, that surface can absorb some of the heat, some of the energy that they have, and those molecules will stick to the surface, and that's called deposition. That can happen. We can also have a gas being converted into a liquid. And that is called condensation. And that's essentially what happens in clouds. This also releases heat. Essentially, the water vapor in a cloud condenses into a liquid into liquid droplets, and now you've got a cloud. A cloud is actually liquid for the most part, liquid molecules, little drops, tiny drops of water that are in the air. And then you can go from liquid to solid. And that's called freezing. Sometimes referred to as fusion. The molecules are fusing together, so that's called fusion. And this one also releases heat. Okay, so these are called phase changes. And we can use those phase changes to separate materials. Okay. So a phase change, for example, suppose we had the following. Suppose we had some salt water. And we want to separate the salt from the water. Okay. Well, there's a couple of different ways we could do that, but one common method is called distillation. Okay, and you've probably heard of distilled water. Distilled water is water that has been undergone a process to separate all of the salts that are in water. So salt water typically has sodium chloride. That's the most common one, but there's some other salts that are dissolved in it. So essentially what you do is you take a container that has the salt water. So this is liquid inside of this container. And again, you add heat. So this is a little gas line, like what's called a Bunsen burner. And we're just going to add a flame. We're going to add heat to the salt water. And what will happen is water boils at 100 degrees Celsius. Okay, 100 degrees Celsius or 212 degrees Fahrenheit. But salt, I'll be a little bit more technical here. Sodium chloride boils at about 801 degrees Celsius. Much, much higher temperature. So as we add heat to the salt water, what happens is the water will start to boil once the temperature reaches 100 degrees Celsius. But the sodium chloride doesn't boil till you get up to 801 degrees Celsius. So as long as the temperature is between 100 and 801, the sodium chloride is not going to boil, but the water will. The water will boil as long as the temperature is 100 degrees Celsius or higher. So what will happen is you just take a little container, a little tube. Okay, so I'm going to draw this little tube over here. And then you have a little container over here. And what you do is the tube is cool. You cool that tube. You could run some cold water around it, or you could put it in a refrigerator or whatever. But the tube here is cool enough so that what happens is the water molecules will boil off. They'll vaporize. This process is called vaporization. And the water molecules, as a gas, will stream through, but now they get cold again and they condense back into a liquid. So there's actually two phase changes occurring. The first one here is vaporization. That occurs inside this container here. The water is being vaporized, but then the water is condensed back into a liquid, right? So gas being converted into a liquid, that's condensation. Liquid getting converted into a gas, that's vaporization. So the water droplets, now that they're condensed into a liquid, will drop back down here and you'll start getting water droplets over here. And so now you'll have liquid water. And if you just keep doing this process long enough, what'll happen is the water will disappear, it'll vaporize. And then eventually you'll end up with salt down at the bottom, right? So you have pure salt down at the bottom, you have pure water over here on the right. And so now you've separated those two materials using this process called distillation. The device itself, the device of boiling the water and separating it from the salt, that's called a still. And the process is called distillation. It's a very simple method. It can also be used for separating alcohol from water, but it works also with salt and with water. Okay. So that's what we would call separation. Okay. So any questions on separation of materials? Cool. Okay, so let me talk about one other type of separation, which is called crystallization. Crystallization is also depends on temperature. So notice that the process we just talked about, distillation, depends on temperature. So does crystallization. So here would be an example. It turns out that if you have materials that are dissolved into a liquid, and I'm going to use water as the liquid again. So imagine you have this cup. It's like a coffee cup. Imagine you have this coffee cup. Okay. And you have, let's do sugar water. Right. We all know that sugar dissolves really well in water. You can pour a lot of sugar into water and it completely dissolves. What we could do is this, let's say this is at room temperature. We would say that the sugar is very soluble in water, right? It's soluble, meaning it dissolves really well. So solubility is the ability of a solute. A solute is something you're dissolving. To dissolve into a solvent. Okay, so in this case, the sugar is dissolved in the water. So we would say the sugar is the solute and the water is the solvent. So, you know, just logically, there should be less solute than there is solvent, because if you put more sugar in than you put water, it wouldn't dissolve very well anymore, right? So the whole idea here is that they're dissolving. If you take those two together, if you take the solute and the solvent together we call that a solution. So this right here, this sugar water, would be considered a solution because it's got more than one material in it and something is dissolved in something else. So in this case, the sugar is dissolved in the water. So that's sugar is the solute, water is the solvent. So we now have a solution of sugar water. Okay. Now, what we can do is we could boil the water off. That would work just like it did with the table salt. But another way to do it would be to take this sugar water cup and put it into a refrigerator. So if we put it in a refrigerator, And the temperature of a refrigerator is around 3 to 4 degrees Celsius. Okay. And what would happen is you would start to see little crystals forming, and that would be the sugar solidifying, and eventually it would fall down to the bottom, some of it. And so we would be separating the sugar from the water. Now, if we went down to an even lower temperature, let's put the temperature like at, right at 0 degrees C. Pure water actually freezes at 0 degrees C, but if you put sugar in it, it won't freeze at 0 degrees C. Even more of that sugar will precipitate out. Okay, so what are we doing here? We're separating the sugar from the water. So if you then poured the water off, just pour the water off, you would have separated some of the sugar from the water. Now, even at 0 degrees Celsius, some of the sugar will still be dissolved in the water, so you won't be able to separate all of the sugar that way, but you can separate some of it, okay? So that process is called crystallization. Crystallization is where a solute is converted into a pure solid. Right, so in this case, the sugar is going from being a solute dissolved in the water to now being a pure solid down at the bottom. And again, as I said, you wouldn't be able to separate the entire amount of the sugar because even at 0 degrees Celsius, some of the sugar will stay dissolved in the water, but you would be able to separate at least some of the sugar in that way. Okay. Let's see here. We can also use, so that's our second method, is crystallization. And I did mute everybody just because I heard some background noise. So if you do have a question, please just unmute yourself and then just ask the question. Okay. So our method, our third method, is to use densities. So densities can be used to separate materials. So, obviously, if you had, let's see, a rock and a piece of wood, we recognize that their densities are different, right? The rock is more dense than the wood. So what happens? What's the effect of that? If you have water, the rock would fall down to the bottom, right? Because it's more dense. The rock has a higher density than the water, so it falls down to the bottom. The wood, however, has buoyancy, right? So the wood has lower density. In fact, it's lower density than water. So in fact, we can use density to separate materials as well. Now, that's pretty simple. We could separate a rock from a piece of wood pretty easily, just physically doing that. But imagine you had 1,000,000 pieces of little rocks and 1,000,000 pieces of little wood, and you wanted to separate them. What would you do? You just drop them all into the water and, like sand, right? Sand is essentially little pieces of rock. All the sand would go down to the bottom. And then all the little wood chips would come up to the top. And then you could separate. In fact, I remember learning in an anthropology class that there was a class of monkeys somewhere, I think they were South America, and tourists or people would throw little seeds on the beach and for the monkeys to eat. But these seeds are like little, but the monkeys were actually smart enough. They figured out that they could just scoop up the seeds with the sand, drop them in the water, and then the seeds would float and the sand would go down to the bottom of the water. And they would just scoop the seeds up off the top there. So what they're doing is they're using density in order to separate materials. We can also separate liquids that way. So density, we're going to talk more about density as we get into calculations. Density is the mass, how much mass something has, which in a sense is a measure of how much material there is, divided by the space that it takes up. And the space, we call that volume. Okay, so for example, if you have a block, okay, so you have this little block right here, we could measure its mass, how much substance there is, and then we could figure out how big it is. That would be the volume. So the size is the volume, and then the mass is how much there is, how much matter. Now, typically, we use symbols for that so that we don't have to write it all out. So mass is a lowercase m, and volume is typically an uppercase v. I don't think there's any rule that it can't be a lowercase, but typically it's an uppercase v. And so what happens then is that it has units. And so the units of mass in chemistry classes are grams, and the symbol for grams is a G. And then for volume, it's typically, it could be different units, and we'll talk more about that, but typically it's milliliters. Oops, yeah, that's hard to, M-I-L-L-I, milli, L-I-T-E-R-S, liters. So grams G divided by milliliters, ml. Typically lowercase m for milli and then capital L for liters. We'll talk more about those units as we get into it later. But this can be useful in the following way. If two liquids don't mix and have different densities, they can be separated using density. I'm going to show you an example here. This is kind of a cool one. In fact, I'll do it with 3 liquids. Imagine we mix water, and water has a density of almost 1. It's really close. I'm going to actually give you the number, though. It's 0.997 grams divided by milliliters at 20 degrees Celsius. So that's a nice 20 degrees Celsius is around 70 degrees Fahrenheit. Nice, comfortable temperature, right? Essentially, we would call that room temperature. So at room temperature, the density of water is very close to 1, 0.997. And I'm going to show you, let's say we have an oil, and it has a density of 0.789 grams per milliliter, again, at 20 degrees Celsius. And then carbon tetrachloride. Now, I'm going to write it out. Carbon tetrachloride. It has a density of 1.351 grams per milliliter. So notice these 3 different liquids. These are all liquids. Water, oil, and carbon tetrachloride. They all have different densities. Much in the same way that a rock or a piece of sand has a larger density than water, so it goes down to the bottom. A piece of wood has lower density than water or sand, so it floats up at the top. The same thing will happen here. The carbon tetrachloride has the highest density, 1.35. Water has the intermediate, right? The medial density. It's in the middle. And then the oil has the highest density. I'm sorry, the lowest density at 0.789. So here's what would happen if you mix those 3 liquids together. Over time, they would separate into 3 separate layers. It's really cool to watch. And what happens is the lowest density is going to be at the top. So that would be the oil at 0.789 grams per milliliter. So that'll make a layer up at the top. This is called a layer. And then the water will be in the middle at 0.997 grams per milliliter. So I'll put little X's there just to show you that that's a different layer. And then the carbon tetrachloride. Now I'm going to write out the chemical formula just so I don't have to write out all those words. Carbon tetrachloride, CCl4. And that one right there is going to be down at the bottom because it has the highest density, 1.351. So notice this is another way that we can separate materials. This is the third method that we could separate materials that we talked about. The first one was the difference in temperatures that things boil at. That's distillation. The second one was crystallization, whereas some materials will precipitate out, form solids out of the liquid if the temperature gets low enough. And now we have the third one, which is the difference in densities, okay? There are other separation techniques out there. I don't want to say these are the only three, but these are three of the most common techniques for separating materials: density, crystallization, and boiling point, essentially, right? Remember, the water had a boiling point of 100 and the salt had a boiling point of 801. That difference in boiling points allows you to separate these materials out. Okay. Awesome. Okay, again, just a reminder, if you have any questions, break in, just let me know. I want to talk a little bit about the idea of pure substances versus mixtures. Okay. And it ends up being a pretty important thing when we move on into chemistry. So let's talk a little bit about that. When we talk about a pure substance, this is really a chemical term. Okay. The chemical term pure substance means essentially that you have what's called an element, or you have what's called a compound. If you have an element, that's called a pure substance. If you have a compound, that's also a pure substance. A mixture is a combination of two or more elements and compounds. So a pure substance is if you have one of them, you have one element or one compound. A mixture is when you have two or more of either compounds or elements. It could be one element with one compound, or two elements or two compounds, or any number greater than two. That would be called a mixture. So for example, salt water. Okay. Salt water is an example of a mixture. And here's how we would argue that it's a mixture based on my claim here. It has water. And water is a compound. And it has a chemical formula, H2O. Okay, so water itself is a pure substance. But it also has salt. And salt is also a compound. Now, what is that salt? It's called sodium chloride. And the chemical formula for sodium chloride is NaCl. So what makes salt water a mixture is the fact that it has one compound, which is called water. That's a pure substance. And a second compound called sodium chloride, another pure substance, right? So individually, water is a pure substance because it's a compound. Individually, sodium chloride is a pure substance because it's a compound. But if you put the two together, you now have a mixture, okay? Another example would be air. Now, I'm not going to look at real air. I'll use ideal air, air that's like kind of what we think of chemically what air is. Air is about 78% nitrogen. Okay. Nitrogen is an element. And I wrote down the chemical symbol for nitrogen, N2. And it's also about 21% oxygen, which is O2. Oxygen is also an element. Okay, we'll talk about the difference between elements and compounds in a moment. Now notice that doesn't add up to 100%. It adds up to 99%. That means there's 1% of other things in there. Carbon dioxide, water, neon, argon, helium, hydrogen. There's all kinds of different things, methane. There's all sorts of things in air. But let's assume that approximately, let's just say that this is air. So it's approximately 100%. Okay. What we would say is that we have an element, nitrogen, and we have another element mixed in with it. They're mixed, right? Those two are together. So when you breathe in air, you can't breathe in just the nitrogen or breathe in just the oxygen. You have to take the whole thing in there. So that's what we would call a mixture. You have more than one element. So a combination of two or more elements and compounds. So you got two elements. And so that would be a mixture. Okay. So air is a mixture, much in the same way that salt water is a mixture. Another example of a common mixture would be, cake batter, right? If you think about it, you got cake batter. Now, cake batter, just to simplify things, we know we have flour in it, right? Now, flour is actually a combination of different compounds. So even flour is a mixture. You've got water in it. That's at least a second compound right there. So if you've got two compounds or more, you have a mixture. You've got salt in there. You've got sugar in there. You've got eggs. Eggs is a lot of stuff in it, right? Eggs has probably hundreds of different compounds in it. So definitely that's a mixture. Okay. Now, let's come back to our distilled water that we talked about earlier. Remember what we did was we took salt water and then we distilled the water. So what we did was we essentially did a separation to make salt. So salt was the residue, the material that was left behind in the container. And then we boiled off or vaporized off the water. So here's what's significant about this from a chemistry perspective. Often what we need to do is the first step of analyzing materials is to separate materials into pure substances. What we did was essentially, when we did the distillation, was we took a mixture and we separated it into pure substances. Okay, so salt is a pure substance because that's a compound. Water is a pure substance because that's a compound. But when the two of them are together, that's two compounds mixed together, we would call that a mixture. Okay, so that's really the significance of this discussion, is that we now, if we put some effort into it, we can figure out ways to separate materials such that they are pure substances. And that is a major strategy, a major concern of people working in chemistry, is to ensure that if they're making some material, they may want it to be a pure substance. They may not want any contamination in it. And so how you make pure substances is an important issue. Alrighty, so let me see if we have enough here. I'm going to actually get rid of that one. Okay, so let's talk a little bit about differences and similarities between elements and compounds. In fact, I'll put versus. We're going to contrast them for the most part. Elements versus compounds. We'll take a look at that. Okay. A little bit of history of elements and compounds. If you look at the first generation of stars in the universe, so imagine you have an ancient star, early 14 billion years ago. Okay. Typically, the first stars were made out of what's called hydrogen. And stars today are primarily made out of hydrogen, but they have other materials in them as well. So hydrogen. Hydrogen is probably the simplest matter that we can deal with chemistry-wise. It's so plentiful. It's around 80% of all typical matter that we understand in the universe. I say typical matter because I mean matter that we understand. It turns out there's matter in the universe that we don't understand. So we'll ignore that for now. It is a very, very simple material. It's called an element. And it has a symbol, and the symbol for that is a capital H. Okay. Now what happens inside of a star is over time, the enormous gravitational pull, because the number of hydrogen atoms in a star is so great that there is a massive gravitational pull due to that mass toward the center. And the atoms start colliding with each other with such an enormous amount of energy. It's just an unimaginable amount of energy because there's so many of them. In fact, in our solar system, the sun is 99.8% of all the mass of the solar system. So all the other planets, the asteroid belt, everything floating in between the planets is only 0.2% of the mass. 99.8% of the mass is the sun. So that enormous gravitational pull, one of the things it does is it produces a new element. Essentially, I'm going to ignore the details here. What happens is one hydrogen atom through a complex steps, more than one step, combines with another hydrogen atom to form something completely different, which is called helium. And helium is its own substance. It's different from hydrogen. And this is the second element that exists in the universe. So probably when the universe started, once enough time had gone by for hydrogen atoms to condense into stars, to gravitationally pull themselves and form stars, the only element was probably hydrogen. And then hydrogen over time in those stars started combining. This is called fusion. And they combined to form helium, a new element, and they released energy. And that's the energy that we receive here on the Earth. All the light that's coming off of the sun, well, I shouldn't say all of the light that's coming off of the sun, but most of the light that's coming off of the sun is because of this process. Two hydrogen atoms fusing into a helium atom, releasing energy, and then that energy reaches the surface of the Earth. Okay? So there's our second element. And what happens is, over time, you start at the center, you start to build up enough helium in the center of the sun or the center of a star that the helium atom will start to react with a hydrogen atom, right? There's still hydrogen in there. And over time, you form another element, which is called lithium, as in lithium batteries, right? This is our third element. Okay. And again, this one also releases energy. So some of the energy being released by the sun is due to this process right here. Again, that's fusion. Fusion is where you take one element and you combine it with another element to make a larger element, a heavier element, okay? So over time, what happens is you start building up heavier and heavier elements. So the lightest element is hydrogen, but over time, you get more and more elements. Okay. Just make sure. So I'm going to organize a few of these elements into a little table. And we'll go over this more later, probably next week. So these are some of the elements that you may be familiar with. Hydrogen, H. Lithium, Li, is in lithium batteries. Na is sodium. So that's the sodium and sodium chloride. And then K is potassium. Okay, so these are some of the elements, and I'm going to number them. So element number 1, the first one to be produced, is hydrogen. The second one, I'm going to write it over here, all the way on the right. Next, in the same row as hydrogen, is helium. And then the third one is lithium, like I said. And then it turns out there's a fourth one, which is called beryllium. And then the next one that gets formed is called boron, which is number 5. And then this is all occurring in the stars. So this is occurring in our sun right now. Some of the beryllium is getting what typically people will call it burned, but it's being converted into boron. The boron is reacting and getting converted into carbon. The carbon is reacting and getting converted into nitrogen, and then oxygen, and then fluorine, and then neon. You've heard of neon lights. So that's element number 10. So it's a sequential process, right? And over time, you start getting heavier and heavier elements. So the sun, although it's about 80% hydrogen and about 20% helium, there's a small percentage of the sun that's lithium and beryllium and boron and carbon and nitrogen, all the way up to iron, okay? And this is potassium, which is 19. And so these are all what we call the elements. And the elements were formed in stars. That's where they all come, except for hydrogen. Hydrogen was probably created in the Big Bang, but all the other elements have occurred within stars. And so one of the aspects of that that's important for us is that the Earth is not really made up of much hydrogen. It's mostly made up of silicon and iron and oxygen. Where do they came from? They had to have come from stars. So that means that our solar system is not the first solar system in terms of history. It had to have come out of a previous star that blew up at some point. Okay, so those are called elements. Now let's talk real briefly. We're just about out of time, but I want to talk real briefly about compounds. So compounds it's a real chemical issue. So in a compound, 2 or more elements can react. Oops. And this is a chemical process. They can react, R-E-A-C-T, to form a compound. So here's an example. If we take the hydrogen element, so this is an element, this is hydrogen. And we combine it with, or we react it with, oxygen. Oops, sorry, I meant to write oxygen. Okay, so those are two elements. So if I had hydrogen and oxygen mixed together, that would be a mixture because I would have two elements, right? Remember, a mixture is when you have one element, one compound, or two elements, one compound, or three elements, one compound. Any combination where you have two or more different substances, different pure substances, we call that a mixture. So if I had a little tank of hydrogen and a little tank of oxygen, and I mixed them together, I just added the two substances together, H2 and O2, that'd be a mixture, just like I said. But something unusual, well, I shouldn't say unusual, but something interesting happens when you combine hydrogen and oxygen in a tank together. Over time, and that time could be very quickly or it could be very long time, over time, they will start to interact with each other to make a new substance. And so what will happen is individual hydrogen molecules and oxygen molecules will react with each other. And that's what we call chemistry, where these different elements combine with each other. And over time, you'll end up with a third substance. And that substance has two hydrogens for every one oxygen. So you'll now have three different substances in there, right? It's still a mixture. You have three different substances, but one of those substances is new. It formed out of hydrogen and oxygen. And what we do is we write what's called a chemical equation. I'm going to write a little arrow to tell us that over time, the arrow is pointing in the direction of time. Over time, a new substance will form. And that new substance is called water. And this is a compound. What is it that makes something a compound as opposed to a mixture? There's three different substances in here, so that's a mixture. But this substance right here, if I were to take it all by itself, if I were to somehow pull it out, and that would actually be pretty easy because it's a liquid. So I just have H2O. That is a pure substance. And the reason we know it's a pure substance is because you can't separate it. You can't boil it to get the hydrogen away from the oxygen. You can't freeze it to get the hydrogen to move away from the oxygen. The hydrogen and the oxygen are connected together in some way, which is called chemical bonding. And so it's a pure substance. We cannot separate. Okay. Can't separate it by boiling or by freezing or by crystallizing. Okay. And so that is called a compound. Now, why do we call it a compound? Because it has two or more elements. It has two elements in it. So any substance that you cannot separate by boiling or crystallizing or by differences in temperature. So these two substances are stuck together. We call that a compound. Okay. So coming back to the beginning of today, we talked about there being two different pure substances. The first one was an element. The elements are a result of what happened in stars. And we give names to them: hydrogen, beryllium, carbon, fluorine. Those are the elements that formed in stars. Those are pure substances if you have just one of them. The other type of pure substance is called a compound. And a compound is what you get when two or more elements react with each other to make a new substance that cannot be separated from itself, right? The hydrogen cannot be separated from the oxygen just by doing boiling or crystallizing or cooling it down to some low temperature. Okay, that's called a compound. So what we're going to do is keep working through this over the next couple of weeks. So chapter 1 is a relatively brief chapter, but next week we'll come back and start working on some new aspects of it. Just as a reminder, make sure you get registered on the Alex and just start running through it. I have videos posted in YouTube. All of that information is in the syllabus. And finally, if you do want to meet with me individually, what you can do is you can shoot me a text. This is all on the syllabus. It's all in my announcements and all that. But you can shoot me a text or WhatsApp or something like that. And I am certainly open to office hours this semester. So we just need to find a time that works out for you and that works out for me. This video will be posted to YouTube probably. I try to do it right after the class. If I don't get it done right after the class, it'll be done this afternoon. Okay. So I want to thank everybody. Thanks for being here. So the next meeting will be next Monday at 9 a.m. I hope you can make it, but if you can't, again, the videos will be posted. And have a great day. Enjoy the beginning of the semester. Hope it goes really, really well for everybody. Feel free to reach out to me, okay? Bye-bye.